Hi everyone, how are you all? Please let me know. You can hear me. Audio, video, everything is fine. You can see my screen, right? Okay. So in this particular session, we are going to see some of the AIMT three questions that we have, we have conducted that AIM three, and then now in this session we are going to see some of the AIMT three solutions. So before I go further, most of you might be knowing me, but still, let me just I'm Sachin. I'm co-founder and instructor at GoClasses. I have done my masters from IISc Bangalore, and after IISc, I have been into Amazon as an applied scientist. I've also achieved GATE All India rank 33. So this is my bio. Okay, let's start with this question, which is related to shortest path and also minimum spanning tree. So this question was a mixed question, okay, which is dealing with the shortest path and also the minimum spanning tree. Let's just see this question, what they are asking, and let's see that how we can solve this question. Okay, what is it? This question is saying that let G be any simple undirected with no self loop or parallel edges, right? So G is a simple undirected graph where there is no self loop or parallel edges with positive and distinct edge weights. So they are saying the edge weights are distinct. Then they are saying let S and T be two vertices in G. Now, which of the following is true, right? So let's just see the first point. Any shortest path from S to T in G must include edge of minimum weight. So they are saying that if you are having any shortest path from S to T, then they must include the minimum weight. But it is not necessary, right? I mean, let's suppose there is some minimum weight which is of 1, and then you are having maximum, I mean, you are having a very big weight. Let's suppose this is 100, but the shortest path could be direct, which is just 2, maybe 3. So this shortest path, which is from S to T, does not include the minimum edge weight. Let me know if that is clear to everyone. See, the shortest path from S to T does not include the minimum edge weight. That's what this option is, and then we are able to make this claim false, right? Because it does not. Okay, I hope you understood this. Now let's just see the second option. What the second option is saying: if the weights of all edges in G are increased by 2023, then any minimum spanning tree in G is a minimum spanning tree in the modified edge weighted graph. So they are saying that if you are going to increase edge weight of all of the edges, then whatever the MST you earlier had, the same MST is going to follow. Is this true? Let's suppose this is S, and then there are some other vertices. Let's suppose A, B, E, whatever, right? A, B, C, D, E, F. Then there might be some MST. Now they are saying that whatever MST you have here, the same MST will follow even if you increase every edge weight by 2023. Obviously, that is true because let's suppose you are applying, like, let's understand this with the Kruskal's. Let's suppose you are applying the Kruskal's algorithm here, and then you are getting some minimum spanning tree. So what Kruskal algorithm will do here? It will just list out all the edges in the increasing order. Let's suppose AB is the minimum edge weight, and then let's suppose maybe ED or something like that, right? But if you increase that every edge weight by 2023, then also the listing will be same, right? So the Kruskals will not differ in any way. So that's why this B is also true. Even if you increase every edge weight by 2023 or whatsoever weight you want, then also you are going to get the same minimum spanning tree, right? What this option C is saying, this is saying the shortest path from S to T is unique. So let's just understand this option C, which is quite interesting option. They're saying the shortest path from S to T is unique. Any shortest path from S to T is unique. So see, it is also not necessary, even though the edge weights are distinct. Okay, even though their edge weights are distinct, but it is not necessary that you are having only unique shortest path. Let's suppose that there is intermediate vertex, which is, let's suppose this is 2 3, and then there could be direct path also, which is of 5, right? So this is not necessary that you are having a unique shortest path between S and, I mean, that's very obvious to see, right? Okay, now let's see the fourth option, which is the only and most interesting option in this among all the options, and that's the reason we have put this question, right? I mean, just because of the fourth option. What this option D is saying, that if the weights of all edges leaving S are increased by 23. So see, they are not saying that all edges, okay? I mean, they are not saying that all edges in the graph. They are saying all edges leaving S are increased by 2023. Then the shortest path earlier, whatever it was from S to T, let's suppose this is the earlier, okay? So let me go to the next page. Let's suppose this is S to T, and whatever the shortest path you had earlier. So this is earlier, and now you are going to increase edge weights from S to of all edges which are leaving S, right? So you are going to increase this edge weight to 2023, which is leaving S. This edge weight to 2023 S. This edge weight to 2023, right? So earlier that was the shortest path. Let's suppose this. Now tell me, won't the shortest path remain same, or it will change? It will change. So this is now. Now this is the situation, and I want to analyze that if this shortest path from S to T will remain same or not. That's the question that they are asking, right? So let's just see if the shortest path will remain same or it will get changed. See what is happening here. If we're increasing every edge weight for 2023, then whatever, let's suppose there are algorithms like Dijkstra and all, but let's suppose I'm just enumerating all the path from S to T, and then we are finding the shortest path between S to T. Okay, so whatever the enumeration you are doing earlier, maybe you will say that okay, this is one of the path. See, yeah, enumeration means you will say okay, this is one of the path, right? And then you will say that okay, this is another path, this is another path that is leading from S to T. But on all the paths, if you compare earlier, let's suppose you have compared, now also if you compare, since the all the paths are going to have the only one this 2023, this edge weight will be different in all the path again, which means that what I'm saying here is that let's suppose that this is some vertex S, and then there is some vertex T. Okay, for example, let's suppose this is the graph that I have. This is the graph that I have. For example, suppose, now tell me how many paths are there from S to D. There are two paths, right? This is first one and this is the second one. Just for the simplicity, I'm just keeping the two paths. Now let's suppose this is the minimum among two paths, right? Let's suppose that this is 1 2 3, but these were 4 5 6. So obviously the shortest is this. This is the shortest. Now, what is the cost of this shortest path? You will say the cost of this shortest path will be how much? Tell me. This will be 3 plus 2 plus 1. Then it will be just 1 plus 2 plus 3. It will be 6, right? This is the cost of shortest path. Now you do what? You just increase this by 2023. This also by 2023. You are not increasing every cost. You're just increasing every cost that is leaving S, right? Now, now tell me what is minimum. Again, this is minimum, right? Because now the comparison is still fair. That's what this option is saying. I hope you are understanding. So Alpha is asking Deepak sir will take decidability part two. It was supposed to be same. Yeah, so that's what I'm saying on the Telegram. On the Telegram, we have communicated the message that it is better that we have the decidability class tomorrow. Reason being is that we could have today only, but reason being is that since tomorrow also you people will not be studying anything new, right? So it is better if we can conduct that tomorrow, and since it is a new day and it is also a good topic, so you will be grasping in more effective way if you do it tomorrow. That's the only reason. Cool. Let me know if you have understood this particular question or not. So they are saying that if the weights of all edges leaving S are increased by 2023, yeah, leaving S if you 2023, then the shortest path from S to T will not change, right? From S to any other node will not change. So that's why this D is true, and then they're saying which of the following is or are true. So the shortest path from S to T is unique. No, that's not necessary. Any shortest path from S to T must include. No, that's also not necessary. If the weights of all are increased, the MHT will remain same. Yeah, so this is also true. So B and D are true. So that was a good question. I hope you understood this. Let me know if there is any confusion. Yes, I will be taking the cash question. Yes, I will be taking. So cash question I will be taking. I don't know question number, but this is the question, right? So I will be taking this question. Maybe after half an hour or so. Just after half an hour. So Satyam is saying I interpreted option D as increasing all the edge weights by 2023, as said which are incident on S. Yeah. So actually, to be very honest, let me tell you one thing, that this particular interpretation, that whatever you did here. So let me just paste this interpretation. So whatever the Satyam is saying, that he is saying that he interpreted this option D just like option B, which means that every edge cost is increasing by 2023. So this interpretation was very normal, because that's how our mind works, right? I mean, our mind actually works in a way that it try to connect the dots and quickly try to find out the answer. But in the examination, that's called the silly mistake. So we should not be doing these kind of silly mistakes. Just be careful about those silly mistakes, right? So when we were designing these options, like I have taken this from one standard university, Princeton University. Okay, do you remember the Hoffman question earlier we did in AIMT 2? So from the same assignment, I have taken this question also. And while I was putting this question, then I was 100% sure that most of the students just will fall in this trap, that this option and this option B and D are same. So that's why I put that option, because I wanted to make you the mistake in AIMT 3, not in the gate. So in the gate, just be with the open minded. Don't do any assumption. Cool. Let's see this question. Let me know if you have understood the previous question, and then we can move forward to the next question. Let's see this question. It is also very interesting question. What they are saying: consider the following possible pseudocode from two processes, where A and B are the block of the code, right? So in all the options, if you see, A and B are the two blocks of the code. Now what they want, they are saying that semaphore is initialized to 0, and then which of the following sequence ensures that A always runs before B? Which of the following sequence ensures that A always runs before? Now, see here A can run, and then B can run. That's fine. I mean, A runs before. That's not an issue. But does it happen always? Can you have, so in this kind of question, just see, can you have B and then A? Tell me if you can have B and then A in this particular option. You can definitely have, right? BA is definitely possible. So since BA is possible, that is why you will say that this is not the correct option. Why BA is possible? Because you can definitely execute this, and then you can execute this A. So BA is definitely possible. That's why this is not the correct option. Let's see this. Is BA possible here? See, can you do down on S? No, because S is initialized to 0, so you cannot run B, right? So since you cannot run B, so BA is not possible here, and A or AB is definitely possible. So that's why B is the correct answer. Let's see this C. Check if BA is possible. A is not possible because it is down as, and B cannot run. So yeah, BA is not possible, but they are saying A always run before B. Here, does A always run before B? No, right? I mean, even AB is not possible. So that's why this is the wrong answer. Because A even does not run. They want A to run. They want A to run. They want A to always run just before B. They don't want A and B to not run. They are saying that A should always run. They are not saying they either they run, or either they do not run, or if they runs, then A always run before B. Right? If they say that, okay, either they do not run, or if they run, then A always run before B. If something like that they say, then C is also correct option. But here none is running, so that's why this is not the correct option, right? Let's see the option D. In option D, can you do yeah, this is interesting. Can you do BA? Tell me, can you do BA in this option D? Option D is little interesting. See, it seems like that you cannot do down. Yeah, that I perfectly agree with you. But you can definitely do up, and then you can print here, right? You can definitely print here. Then you can go here, and then you can do B, and then you can do A. So basically, BA is definitely possible here. C is possible here. That is why this is also a wrong option. Let me know if you have understood this. Yeah. Okay. So I hope you understood this. Cool. Now let's just move to the next question. In this question, what we have asked, consider the following possible data structure for the set of n distinct integers. Okay. A mini heap array of length n sorted in the increasing order, which means 1, 2, 3, 4, like that, right? N. And a balanced binary search tree. So, for which of the data structure is the number of steps needed to find the remove seventh largest can be done in log n in worst case? Tell me in which of them can be done in order of log n. So, if it is a min heap, then it means one will be on the top, right? One will be on the top. You want the seventh largest. So, you don't know where is the seventh largest, right? I mean, see, it is a mini heap. So if it is a mini heap, then the largest elements are not basically can be effectively found out the mini heap, right? Mini heap is designed for minimum element. So the seventh largest could be anywhere, uh, could be anywhere from maybe like I mean could be in the bottom, or maybe like I need to actually see exact place, but it can definitely be on the bottom, right? Since it can definitely be on the bottom, that's why you will say that that it will be taking, I mean it will be taking at least order of n. I mean, since it can be on the bottom, right? It can be on the bottom also. That's the point. Now let's just see where it can be at the maximum. Tell me, tell me, can it be on the bottom? Seventh largest in the main heap. Seventh largest. Seventh largest in min heap. Can it be on the bottom? Yes. Can it be on the second place? I think yes, right? It can be here also. Because if it is here, then I just need two more elements which are basically, see, this is in the increasing order, right? This is increasing order. I told it many times. This is increasing order in case of min heap. Now, now if you have here, if you have something here, then you need two more elements. So yes, seventh largest could be here because it is greater than six elements. It is basically have six elements which are greater than this, right? There are six elements which are greater than this, the seventh largest. So you can have some element here, and there are two elements which are greater than this, right? So yeah, that's why seventh largest could be here. I hope you understood. Seventh largest could be on the second position. Tell me, can it be the third position? If it is in the third position, then I think below this there are one, two, three, four, right? Five, six. Yeah, one, two, three, four, five, six. Yeah. So there are six elements, and then this is, since all elements are distinct, so this is basically greater than. I mean, there are six elements which are greater than this, so that's why it could be on the third level also. Getting my point? See, there are there are six elements. There are six elements which are actually one, two, three, four, five, six. There are six elements which are greater than this. That's why it could be here also, because the seventh largest basically have six elements which are greater than this, right? So it could be here also, and I will accordingly I will adjust these numbers. So it could be here also. Tell me, can it be here? Can it be here? Can it be here? If it is here, I need, I think, many elements. 1, 2, and then uh, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I mean, there are total 15 elements. I need 14 elements which are greater than this. And since I do not have, that's why it cannot be. See, every element here, since it's a mini heap, then a part of this is also heap, right? I mean, that's how the heapify works. So basically, if the seventh largest I put here, I need 14 elements which are greater than this. Since I do not have the 14 elements which are greater than this, that's why the seventh largest cannot be here, right? So this can also be a gate question, that where can be the seventh largest. So seventh largest can be at the bottom. Seventh largest can be at here, because if I'm putting here, then I just need two more elements which are greater than this. So it can be here. Can it be here? Yes. If I put it here, then I need total. See, this is, it works like this, right? One, two, and then sorry, yeah. So these are the two elements. So 1, 3, and then 2 power, or maybe let me write like this: 2 power 2 minus 1, 2 power 3 minus 1, 2 power 4 minus 1, something like this, right? 3, 7, and then this is 15, like this. So basically, if I put the seventh largest here, if I put it here, then these are the total three elements. So I just need two more elements which are greater than this. I do have two more elements which are greater than this. So that's why I can put it here, right? See, let's suppose there are numbers which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which is seventh largest here? I think this is first largest, second, third, fourth, fifth, sixth, seventh. Right? 4 is the seventh largest here. Can I put 4 here? Yes, because I have the greater numbers here, right? I have the greater numbers to fill, so that's why I can put 4 here. Can I put now similarly, if I just ask you, can I put 4 here? Can I put 4 here? Yes, because I need the greater number, 5, 6, then 7, 8, 9, 10. Yes, I can easily put here. Because if I put in 4 here, then I can fill the remaining places. That's the key point, right? Now tell me, can I put this 4 on the above level? Can I put this 4 here? If I put this 4 here, then I need, since the including this are there are 15 elements, right? Including this have 15 elements, then I need, I think, around 14 elements, right? Around 14 elements. So if I need 14 elements, then I don't think I can keep it. or at least maybe let me actually I need to see it. Um, Actually I need to see whether the is full or not, right? I mean I might not be needing last level to be full. So basically we need to do some analysis here, and then we need to find out the answer. Okay. So minimum heap. The key point here is that seventh largest can be here, right? Can be here. Since it can be here, that's why order of log n might not be sufficient for me, right? Because in heap I cannot guarantee that these elements are in which order. In heap the siblings are of not any order, right? In heap the siblings, these siblings have not no relation between the siblings. You can do one thing, which means you can have uh you can have, let's suppose this is one, you can have this two, and then you can have a very big number here, maybe 1,000, something like this, right? So basically the siblings do not have any relation in the heap. But yeah, the ancestor and descendant have the relation. So maybe you can say this is 1,000, and there is some other मतलब एक अलग ही इसकी दुनिया चल रही है, which means this is 1,001, this is 1,002. There is some other word for this, there is some other word for this, right? There could be two different words, right? I mean, this could be some other word, this could be some other word, which is 3 4. These are very less numbers, these are very big numbers, so it could happen. So in mini heap there is no relation between the adjacent, between the siblings. So that's why, like, you will say that that the seventh largest could be here, since you do not know there is any relation between them. So that's why, like, if you know by chance, let's suppose these are sorted or something, then maybe you can do it in log n or something, right? But since you do not know that these are the sorted, so sorter or something, so that's why, I mean, these are the sorted, so that's why you have to spend order of n. Now, the array of length n sorted in the increasing order. Yeah, that's interesting. If you have the array which is sorted in the increasing order, so 1 2 3 4 5 6 7, right, like that, right, till n. So suppose it is sorted in the increasing order. Now let me make it little clear. Let's suppose you have some array, and here you have 1 3 4 till n, right? Now since it is increasing, this is increasing order. If you want to find out the seventh largest, where it will be? Definitely it is from this last, maybe you can say that n minus 7 plus 1 or something, right? I mean, you can easily find out the index of the seventh largest in just order of 1. Just order of 1 you can find out the seventh largest. Sahil is saying this, sir, how to approach question like minimum number of heaps possible with n. I think I have taken some YouTube session for this, exactly. If I have taken the YouTube, actually in the course we have done it very nicely. If there is some go classes student, then they can say, in the course we have done it very nicely, but on the YouTube I think we have not put any video regarding this. But yeah, in the course we have done minimum number of feet and all, very nicely so you can do it in order of 1, but they are saying in order of log n. Yes, see, in order of log n, it means that it is less than or equal to log n. Since you are doing in constant time, that's why it is also order of log n. Okay. So this is very important to understand. The order of log n does not mean that log n exactly. Theta of log n means log n exactly, but order of log n means less than or equal to log n. So that's why you will say that, yeah, in min heap you cannot do it using this. And similarly balance minus ht, if it is balanced, then if you need to find out the seventh. Okay. It is also interesting. See, if it is balance minus ht, then you know where is the seventh largest, right? What you can do, this is the largest, right? This is largest. This is largest. This is the third largest. This is the second largest, right? I mean, we have done one of the problems something like this. So this is largest. This is um, this is third largest. Now where is the seventh largest? So you have to do one thing. You have to basically find out the seventh largest. I mean, you can find out the index of seventh largest just using some computation. I mean, you don't need to basically traverse the entire array or the entire tree. You can do it in just order of log n. Okay. So n is asking if elements are repeating or that. I have discussed this many times. I mean, in just DS marathon we have discussed it. If elements are repeated, does not matter. See, even if elements are repeated, I think in case of heap you are asking, right? Even if elements are repeated, then also the maximum will be on the leaf. It could be here also. See, let's suppose this is 100, then 100 must be on the leaf, right? And then it could be in between. Since it is repeating, it could be in between. That's not of our interest. If 100 is there, it must be on the leaf also. It could be here also. See, we have discussed this in the DS marathon very nicely, the heap and all. So you can watch the DS marathon. Cool. So in case of balanced binary search tree, it is also very very interesting. Now, what do you think? Do you need to spend order of log n to find out the I mean order of n to find out the seventh largest, or you can do it in just log n if there is a balanced binary search tree? If there is a balanced binary search tree, then as I said, then what you can do, you need to find out the seventh largest. To find out the seventh largest in this balanced binary search tree, you can basically find out the index of the seventh largest without traversing all the array. Okay, so you can definitely find out the index of the seventh largest, and then you know that where to stop or where not to stop. Okay, so that's why I think D is the correct answer. Cool. So now I think this question was very easy. Let me know if there is any doubt here. See here, I just wanted to tell you that if they're asking about the time complexity, you do not need to multiply by the 4 here. Okay, 4 into t n minus 1 is, should not be the case, because you are calling just fn minus 1 just one time. So that's why it will be the time complexity will be tn minus 1, because you are calling it one time, and then you're calling n minus 2 one time, and then some constant amount of work always is there, right? In array we have to remove also. No, we don't need to. I mean, even if you remove or something, since it is sorted, right? Even if you need to remove it, then there are only 6 7 elements here, right? 6 7 elements here. So it will just take constant amount of time to put the 6 7 to just do the sifting. It is not the sifting that you have to do from the beginning, right? In the end, since there are just six elements, if you want to remove it, see they are saying find and remove. Yeah, find and remove, they are saying. So not an issue. Even if you want to remove it, it doesn't take any work. So I hope this question is also very easy. I mean, what you need to do, you first need to write the recurrence. So see, since they are saying they are using the recurrence only at this level, so you can say tn equal to, this is first third of the silly sort, which means tn equal to tn by 3 plus heap sort is going to take n log n, but it is on the two-third of the elements. So basically it will be 2n by 3 log 2n by 3, which is just n log n, right? The constant does not matter. This constant does not matter. And then see, this is 2n by 3 into log 2n by 3. This is same as n log n. Why? Because if there is like I told in the data structure in the course, if there is anything which you can write c into function, right? C into function. This is same as function. Now let's just see if you can write this as c into n log n, and then only you can say it. Otherwise, obviously you cannot say it. So let's just see if you can write it c into n log n. So what you need to do, 2 by 3 into n into, I mean this 2 by 3 is just redundant, so you don't need to worry about the 2 by 3, but maybe this 2 by 3 you may need to worry, because this 2 by 3 does not matter because it is just a constant to function. So that's why you can definitely remove this 2 by 3. Okay, so this 2 by 3 is not of our interest, but this 2 by 3 which is in the between, this might be little interest to us. So let's just see if you can remove this 2 by 3. So what you can do, this plus log n, right? This is what you can do. I mean, this is just multiplication of this, and since this is a plus, in the plus you are writing some function, so that's why you can also ignore this. So finally, it is n log n only. Okay, so n log n plus some constant. So you can solve this easily using the Master's theorem, and then I think finally you will be getting. You can write it n power log base b. Base b is 3, a is 1. So this is n power 0, which is 1, and then n log n. So finally you will be getting n log n. Using the Master's theorem, you can do it. That was easy question. You should have done it. Let me know if you have done it correctly in the exam. There was some confusion. I don't want to keep this session very long, so that's why I'm just moving to questions, every question little fast. So let me know if there is any doubt. I will stop. If there is any doubt, I will definitely stop. Otherwise, just let me know if you want some more clarification. Okay. So this question was little interesting. What they said, they have given some initialization. So they are saying that this is some initialization, and you want to print the hello world. So let's just make the diagram first. What does this mean? What's is an array, right? If you have seen C programming from me, then you should be very comfortable. Otherwise, that's also okay. I mean, if you have done it from anywhere else, then you can draw the diagram. This is hello. By the way, you know that in which memory these strings are. This string and this string is from the static area, right? And this verse is from the stack area. This is from stack, and these strings from the static area. Okay, this V is something which is pointing to this words, right? That's what it is given to us. I think I have the diagram on the next page. Maybe I make use of. Let me know if the diagram is okay to everyone, and then we will see that how to print the hello world. See, now this V is a void pointer, right? Now, since it is a void pointer, it can hold any address. Now it is up to you how you want to use this particular address, which means that you can't do directly star B. Okay, this is not allowed in case of void pointer. In case of void pointer, this is not allowed. But what you can do, you can typecast it and then you can use it in any way. So star B directly is definitely not allowed. Now let's just see. Let's just see that how we can print the hello world. Suppose I just typecast this V. Okay. So see, these are the locations here. 2000 is written here. 3000 is written here. Now suppose that I just typecast this B as an integer. I just say that okay, this is the integer typecast that I have here for the V. Then what will happen if I then okay, now it is this one box, it is one pointer which is an integer type pointer. Now if you do star, what will happen? It will say that whatever V is pointing to, this should be treated as an integer. And if you do star, then most probably, let's suppose that integer size and I'm not making it complicated, that address size, integer size, or these things. Okay, let's suppose the address size and integer size is same. Actually, this is the address 2000 integer address, and then let's suppose these two sizes are same, and if they are different, then also it can give you 2000. It depends on little Indian, big Indian, these things, but let's not worry about it. Basically, let's just assume that these sizes are same. If you're doing using that as an integer, then it will putting the star will give you 2000, right? Which means that you whatever you are pointing to, it is saying that treat this as an integer, treat this that an integer, that this is an integer, and then if you put the star, you will be getting 2000. But that's not what you want. You want to print this hello. You want the address of this h, right? You want the character address. So what you will be doing? Okay, tell me what you will be doing. Can you treat this as a character? If you treat this as a character pointer, if you treat this V as a character pointer, you put the star, what you will be getting? This ultimately, this is what? This is, can anyone tell me the type of this? Okay. I mean, see, if I write int x, what is the type of x? What is the type of x? This is just integer, right? Similarly, I'm just asking you that if you write char star p, and then you put let's suppose you put one more star, then what is type of this whole expression? Can you tell me? The type of this whole expression will be, anyone quickly? See, this V is getting typecasted with character pointer, and then you're putting the star. So which means that this type of this is basically just a character, because it type of this is character pointer. See, if you write int star p, let's suppose if you write int star p, if you and then you write p equal to address of x or something, and then you do star p, then what is the type of the star p? This is the integer, right? Because p is an integer pointer, you put the star, it will become integer. This is the character pointer, you put the star, it will become character. So, so you don't want this, right? What you want? You want ultimately, if you want to print it, you want the ultimately whatever you have here, you want the address of that, right? You want the basically pointer to character. Basically, you want the address of the character, not the character. So basically, if you write it, then it will not be successful. Why? Because it will just give you the character. I mean, whatever the first byte is there. So basically, it will not even fetch you the 4 bytes. What it will do, let me tell you what it will do. See, this v, see here. Let's suppose if you write the earlier expression, which is char star, then tell me what is the result of what it will do. It will say whatever v is pointing to, treat this as a character, and this star will say that I will give the first character. First character means first byte. So first byte means whatever 2000 binary is. So can you tell me what is the binary of 2000? Binary of, let me just give you the binary of 2000. And you need to represent, let's suppose this is the binary of 2000, you need to represent that binary in the 4 bytes, because integer is of 4 bytes. Now it will depend whether you are using the little Indian, big Indian, but let's not worry about it. This 2 bytes, then 3 bytes, one. These are the 8 bytes, right? Now, if you fetch using the star, it will just give you the first byte, which means it will just give you 0. Is it of your interest? See, if you just do star of this, it will just give you the first byte, which is what we don't want, right? Which is what we don't want. So basically, what we want the address of h. So what you will do, you will treat this as a double pointer, because this is void, and in whatever way you can treat it. Basically, you want this particular v to point. Basically, this v is pointing to. Like logically, it is pointing to some array. So v is basically pointer to v is a pointer to the first element of the array, not the array itself, right? To the first element of the array. So what is the first element of the array? It is a character pointer. So it is basically pointing to first element of the array. In other words, if I want to write, I can say v is a pointer to um, first element of the array is basically a character pointer, right? It itself is a character pointer. It is pointing to the character. So char pointer. So v is a pointer to char pointer, which means v is a double pointer, which is SMS saying v is a double pointer. Let me know if that is clear. So that's how you want to treat this b, right? Okay. So I hope you understood. Cool. So basically, you want to treat this v as a double pointer, and then I think the only option which is matching is this one. V is the correct option. Let me know if you have liked this question. I mean, the question was simple, I agree, but all the questions were in AIMT were we kept it up to the gate standard, which means we have not made it unnecessarily tougher, but we just wanted to convey the concepts, some small concepts in every of the question. In every question, you will be finding some small concept, right? Okay. Now let's just move to the next question. Okay, yeah, that is done. Let's just see this question. This was very nice, easy question. What they are saying, the page table lookup is given to us, which means they are saying the virtual page and the actual page that is given to us, which means this virtual page number 0 is mapped to the actual page number 3, which means what? That you have the physical memory or the main memory. Let's suppose that there are This is page number 0. Let's suppose page number 1, 1, 2. So let's suppose these are the page number. In the main memory, these are the page numbers. 1, 2, 3. And let's suppose there is one more page number. Page. The main memory, let's suppose there are five pages. This is page number 4. This is the main memory. Now they are saying that you have your process, you divide your process into number of the pages, and the page number 0. Okay, let's suppose this is the page number 0. It has gone to the page number, the physical frame number 3. That's what this mapping says, right? The page number 0 has mapped to the physical frame number 3. Similarly, the page number 1 is not mapped to anything. Maybe this page number 1 is actually the empty area. Do you remember the empty area between the stack and heap in the process? This is empty area, right? This is stack. So maybe there is nothing there. That's why you have not mapped to. Or even if something is there, then let's suppose it is currently not mapped to. You put it on the disk, right? It is possible that you put it on the disk. Put on the disk. That's what the demand paging says, right? This is basically a concept of demand paging. Demand paging means you do not need to map every page to the main memory. You just map whatever is required. So anyway, the question is very easy. What they are saying is that, like, if the address is given something like 0 comma 514, they have given that what does this 0 comma 514 mean. I mean, this is well standard question we have taken from some university. So it is like they have defined everything. What does the 0 comma 514 mean? It means that p comma d, it is saying that page number 0, right? The page number is 0 and displacement is 514. Page number 0 means it must have mapped to actual page number 3. So the actual page number 3, which means this is page number, let's suppose this is page number 0, 1, 2, 3. So here this page is lying, right? This is the main memory. Here this page is lying. So before this page, there are three pages are there, or the three frames are there. So basically you will say that if the page size is 1024, then 3 into 1024, these many bytes must be there, and then plus some displacement is also there, right? What is the displacement? They have given the displacement plus 5. So that's how you can calculate the C is the correct answer. Okay. Let's do this question. What this question is saying, suppose we roll two distinct tetrahedrals, four-sided dice. So basically that there are two distinct dices. This is dice 1, this is dice 2. This question was of 1 mark or 2 mark. I do not remember. I think it was for 1 mark. Okay. Can you just tell me it was for 1 mark or 2 mark question that we are currently solving? I can also check. Okay, it was for 1 mark. So, let's just see this question. Like, why I'm saying it was for, why I'm checking, because this was easy question only. Like, I just wanted to know whether we have kept it for 1 mark or 2 mark. So each dice contains some number. This dice can have 1, 2, 3, 4. This dice can also have 1, 2, 3, 4. That's what they're saying. And then they're saying X with the number of the dice that shows, okay, an odd number, which means if both the dice are showing 1, 1, then X could be 2. If both the dice are showing, let's suppose 3, 3, then also X is 2. If one dice is showing, let's suppose 2, another one is showing 1, which means one is showing even, one is showing odd, then in that case X will be 1. X is the basically telling how many dices are showing even number, and Y is telling you how many dices are showing the odd number, right? So so both can be of 0, 1, 2, which means that if X is 0, which means 0 dices are having even number. If X is 1, then 1 dice is even number, something like this, right? Similarly, X can be at most 2. If X is 2, which means both dices as even. And it is very clear that X plus die, since it is also number of dice which are having even number of dice which are having odd number, X plus Y must be 2. Actually, in earlier, like when I put this question, I have also given that X plus, note that X plus Y is 2. Like that I have extended this line. Note that X plus Y is 2. Then later, I and Deepak discussed. Then we came to the conclusion that let's not give this also as a hint. We want to give you this as a hint earlier, but then at the last moment we decided that okay, let's not keep this as a hint, because the reason is that like we don't want to. Um, I mean, we actually wanted to think these small things. So that's why. Okay. So what they're saying, probability that y is greater than x. What does this mean? Y is greater than x means that y can be 2 and x can be 1, and there is no other way to get y greater than x, right? Which means, sorry, x cannot be 1, x must be 0, because x plus y has to be 2. So I think that's the only possibility, because x plus y has to be 2. So see, there are x and y can take 0 1 2 values, 0 1 2 values, right? So if x is taking 0, then y must be taking 2. If x is taking 1, y must be taking 1. If x is taking 2, y must be taking 0, because x plus y is actually 2. So these are the only three combinations possible for for x and y. Now we are saying y is greater than x. Y greater than x means they are talking about this case where probability of y greater than x is same as saying probability of y equal to 2 and x equal to 0, right? That's the same probability, which means both of the dice has the even number or the odd number, whatever. So I think y is for the even number. Okay, both of the dice have the even number. Okay, x is for the odd number. Anyway, does not matter. Y is for the even number. So ultimately, it is boiling down to one thing, which is saying that y must be 2 and x must be 0. So which means both of the dice must be having the even number, which means that there are two even numbers here, there are two even numbers here. So basically, there are four combinations which are favorable to us out of the 16 combinations. So that's why the 1 by 4 is the probability. Easy question, right? Okay. There is nothing in this question. We are having two dice. They are just asking that what is the probability of y being 2 and x being 0? Or in other words, y is greater than x. Which means what is the probability that both of the dice has the even number? See, there are two dices, dice 1, dice 2, and then this dice is having 1, 2, 3, 4. This dice is also having 1, 2, 3. They are asking what is the probability that both dice has even number. That's what they are asking. Like in other words, so what is the probability that both dice have even number? Like we have, there are two even numbers here. There are two even numbers here. So there are four favorable cases out of 16. So that's why this is 1 by 4 probability, right? This question was quite easy. Let me know if there is some doubt here. It is just that they're playing with the random variables, the confusion or the definition with the random variables. Otherwise, this question was actually very easy. Okay. Now let's do this question. This question is most debatable question that I found in our AIMT. This question has got highest views in just 2 days. It has got 720 views, which is considerably quite good, right? In this AIMT, I think there were more than 1,000 students. Like I need to check it correctly, but yeah, there are couple of lot more students than AIMT 1 and 2. And then from this views only, you can see that okay, there are only 720 students has watched or has seen this particular question. Then must be there are more than 720 students. Okay, anyway, let's see this question. What they're saying let a node x is a part of the network running a distance vector routing protocol. X has three entries in this routing table. So x has three entries, which is w y z. Now the cost is also given, next hop is also given. So what they're saying that if you want to go from x to w, then the next hop is w itself, which means you can go in the cost of 4. If you want to go from x to y, then you have to go via z. You have to go via z. You want to go from x to y. That's fine, which means maybe via z. If you want to go to z, then you will be going via w. Okay, so via w you will be going to the z. And if you want to go to the y, so you have to go via z. So basically, see, I'm writing everything. See, they have said like if you want to go to w, you must go directly. If you want to go to y, then via z. If you want to go z, then via w. So if you want to go z, then via w. If you want to go y, then via z. So basically, via z means you will be first going to the z in whatever way possible, right? And then from here you will be going to the y. So basically, if you want to go to the y, then must be going. So these are the shortest distance that they have given, right? I mean, if you want to go w, go directly. If you want to go to the z, then go via w. If you want to go to the y, then go via z. So basically, these are the shortest distance which are given to. Now, what they're saying is that alpha beta are the unknown values, unknown to you, but not to x, which means like x knows what are the alpha beta. Assume that the distance vector routing protocol has converged and the minimum cost path from x to every other node has been found. The given table contains the cost after the convergence of the algorithm. So they are saying that we denote this cost of x to y as a direct link. So which means that if you want to say the direct link, they are saying cost of x to y. And then if you want to find out the minimum distance, then they are denoting it by d of xy. So this c of xy is basically the cost of direct distance of direct, and then d of xy basically cost, minimum cost from x to, okay. And then they have given that we know that cxw is 4 and cxz is 10. So basically there are two data that they have given. One is this table, another one is that line. Okay. So using these two, we need to find out the distance from W to Cool. So see, they are saying that from this X, if you want to go W, go directly. I mean, this is the shortest, which is a 4. So which means that and like this cost is also 4 and minimum distance is also 4. That's fine. Now X to W is given to be 4, which means like I mean the cost is given to be 4, and then you can go directly. If you want to go from I mean there is a link from X to Z, which is of 10. Z, this is of 10. X to W is given to be 4, and this is also shortest. That's okay. I mean from this you get to know this is shortest, but from this line you get to know that these are the direct links. So I'm just drawing the direct links. Okay. So these are the direct links which are given to us. Now we need to check that what is the distance from W to Z. I mean, what should be the minimum distance from W to Z? Now see here that this they have said that this is the minimum distance. Like if you want to go from X to W, this is the minimum. This is the shortest from X to W. Similarly, they have said if you want to go from X to Z, then you must go via W, right? You must go via W, which means like they have said like this is also shortest. I mean, you will first go to W, and then from this W, you will be taking the minimum distance from W to Z. So basically, this is also sorted. What do I mean? This is X. They said like if you want to go to W, this is the shortest. If you want to go to Z, then you first go to W and then take the shortest. Obviously, you will be taking the shortest from W to Z. You will be taking the shortest from W to Z also, and then ultimately you will finding X to Z as a shortest. This is what they are saying, that if you want to go to W, take this directly. If you want to go to the Z, then take the path via W. So if you're taking the path via W, then obviously you will be taking from this W, you will take the shortest, right? So what I'm saying here is that this is shortest, that's fine, right? This is shortest because that is given to us. And then they're saying if X to Z do you want to go, then go via W. So this is also shortest, right? And if this is shortest, then this shortest is anyway given. Then actually, if X to Z is shortest, then any sub vertices, any sub path which is X to W, W to Z, that has to be shortest. This is also shortest. And then they said like okay, from X to Z you have a path of length 10. I mean this is a direct link. Now tell me what it can be. Okay, what is the shortest distance from W to Z? Can it be 5? Can it be 5? Okay, let me just say, let's say that can it be 1? Can it be 1? Shortest distance from W to Z, can it be 1? Tell me, can it be 1? It seems like it can be 1, right? Seems like it can be 1. Why? The reason being is that, I mean, there is no limitation. Like, I mean, it can be as shortest as possible, isn't it? Can it be 1? See, it can be as shortest as possible. Why not? In the table they have given, let me just also write the table, because the below information which is 4 and z I have written, but let me also write the table here. In the table they have said, like, if you want to go from x to w, you take the direct path. If you want to go from x to z, you take via w, right? If you want to take via w, then from this w obviously you will finding the shortest. So can it be 1? And definitely it could be 1. But there is a small issue here. If that is 1, if that is 1, then there is a small issue here. The issue is this line. See, they are saying, if you want to go to y, then go via z. So if this is 1, then x to z will be 5, right? I mean, this will be 5. This shortest will be 5. And then they are saying, if you want to go via go to y, okay, then go first to z directly and then go to y. They are saying this is shortest. They're also saying that this is shortest, right? They're also saying this is shortest. So if it is one, then you must be going to Z directly. Not directly. I mean, via W, right? See, what they are saying. What are the shortest which are given to me? X to W shortest given directly, and then you do not know what is W to Z, right? You do not know. Then this is 10 which is given to me, 10 which is given to me, and then they are also saying that this is shortest. So basically, this shortest is given to me. This is also shortest. They are saying this is also shortest. It is 4. They are saying this is also short. This is the problem here. I mean, not the problem, but yeah, this is the question. They are saying this is shortest and this is shortest. Then they are asking this one. What is the shortest between W to Z? That is the question, right? Okay. Let me know if the question is clear to everyone. See, given that this is shortest, I mean, in the table they have said, like in this table, they have said that if you want to go W, go directly, which is shortest. If you want to go to Y, go via Z, and which is shortest, right? And then go to Y. And then if you want to go to Z, then go via W. Okay. They are saying if you want to go to Z, then go via W. This is what also they are saying. Now tell me, since this is shortest, tell me what it could be. Can it be 1? If it is 1, then this ultimately this will not be shortest, right? This will not be shortest, because then this will be shortest. So it cannot be 1. Can it be 5? No, because then this will be shortest. Then ultimately, if this is shortest, then for that at least it should be 6. It can be greater than 6. Can be greater than, sorry. Okay. It cannot be greater than 6 also. We will check. So okay, tell me, can it greater than 6? Or let me first talk about the 6. But before that, I just want to know that if you are getting my point, like, I mean, what I want to ask. See, the question is about, they're asking the maximum possible value here. They're asking the maximum what it could be, right? So maximum this could be 6 definitely. Why? Because if this is 6, then I'm not violating the thing that from X to Y, this is shortest. This is still shortest, right? This is still shortest. Now tell me, can it be 5? Can it be 5? Let's not worry about the maximum and minimum. Can it be 5? Let me know. See, if that is 5, then the ultimately this will be shortest, right? But they are saying that if you want to go to y, then go directly. If you want to go to y, right, go to z, not don't go to w. So if you like if you want to go to y, then first go to z. That's what they are saying. So if you keep this also 5, then it will be a problem, because then this will be shortest, and that's what we don't want. So that's why this must be 6. This must be 6. Now can it be 7? Can it be 7? This is my question. Okay. This is interesting. Tell me if that can be 7. See, if you put this 7, the minimum distance from W to Z is, let's suppose you're putting this 7. Let's suppose somehow it is 7. Is this possible? Why this 7 is not possible? Okay, so you guys are saying that 7 is not possible. Why? Why that is the case? So what will happen if I put this 7 here? Let me just check. Distance to Y will not be satisfied. No, if you want to go to Y, then you will definitely be going via this path. You don't worry about this path, right? If you want to go to Y, then you are going directly to via Z. If you want to go to W, you are going directly. If you want to go to Z, then you are going via W, right? Yeah, that is interesting. So see, this cannot be 7 also, because if that is 7, then then if you want to go to Z, they are saying go via W, go via W. If that is 7, then ultimately what will happen? Then you will not be you will not be going via W. You will be going via direct path, which means this. See, they are saying that if you want to go to Z, then go via W. Okay. So okay, that's ultimately a very nice question. See, this cannot be more than 6 also. If this is more than 6, then what will happen? You will not be choosing this path, right? You will not be choosing this path. You will be choosing this path to go to Z. But they are saying that choose this path. See, they are saying that if you want to go to Z, if then go via W. For Z, they are saying choose this path. For Y, they are saying this choose this path, right? For Z, they are saying this is shortest. For Y, they are saying this is shortest. Now, if you keep it 7, then why will you go directly? I mean, why will you go via W? They are saying that this is shortest. Since this is shortest, it cannot be more than 6. It cannot be. It must be lesser than 6. Lesser than equal to 6. Must be lesser than equal to 6, because you are choosing via W. You want to go via W. So this must be lesser than equal to 6. But now again, can it be? Can it be 5 also? That's my question. If it is 5, it will be a problem again. See, it cannot be greater than 6. Reason being is that then you will be not going via W. Like the moment you put it 7 or something, or maybe 6.1, 6.2 or something, right? Then you will be not going via W. You will be going directly, because it is 10 that you are having. So you cannot put greater than 6. You have to put less than equal to 6. In the less than equal to 6 also, I mean the maximum could be 6. That is fine. You cannot put it. It has to be exactly 6 actually, right? You cannot even put 5. Why? The reason, if you put 5 here, the moment you put 5 here, then X to Z, this will be shortest, right? I mean, actually, I want to have a tie between these two paths, because if you put 5 here, then you will, if you want to go to Y, you will not going directly. I mean, you will be not taking this path, right? Why you will take this path? You will be going like this. So basically, it cannot be even 5. It cannot be greater than 6. It cannot be less than 6. It has to be equal to 6. So I can even ask the exact value here. It has to be equal to 6, right? I hope you understood this. See, let me just break this down again, this problem into two parts. So what they are saying that this is shortest given to you, right? And then this is also shortest that is given. So these two are shortest given to you. So basically they are saying this is shortest, I mean, if you want to go to Z, go via W. If you want to go to Y, then go via Z. That's what they're saying. Let me not attack this problem directly. Let me ask you something. Let's suppose this is X, this is Y. Suppose you know that this is shortest. Okay, suppose you know this is shortest, and there are some vertices in between. Then tell me, won't this X to A is also shortest? Because if this is not shortest, something else is shortest. Okay, something else is shortest. Then I will go via that path, and then ultimately will not be shortest. What I'm saying is that suppose you know this is shortest. Let's suppose this path cost is, let's suppose 10. Okay, let's suppose this is given to you. That's very important that you already know this is shortest. Okay, then I'm asking, can x to a, let's suppose 5. Okay, and then this is 2, this is 3, or something like this, right? So suppose this is the case. These are the edge cost, and then suppose you know this is shortest, that x to y is shortest to be known as 10. Now I'm asking, can this be lesser than 5? I mean, can there be other path which is lesser than 5? Suppose that is the case, that is 4 or something, or maybe 5, 4.9, 4.8. I mean, lesser than 5. Then ultimately this will not be shortest, right? This will be just lesser than 10. So since I know that this is shortest, so that's why every piece you pick here, is also shortest. Every piece you pick here is also shortest. Let me know if that is fine to everyone. Okay. So I hope that is fine. That every piece you pick here is shortest. But vice versa is not true. Which means, let's suppose this is known to be shortest, x2 is known to be shortest to be 5, and a to b is known to be shortest, maybe let's suppose this is 4. X2 is shortest and a to b is shortest. You plug both of them, and then can you say that x2b is shortest? Can you say x2b is shortest? May not be. Directly it could be like, let's suppose 3. Basically, if you know that two are shortest, you plug them together. You don't know. Ultimately, you will be getting shortest or not, right? So basically, I mean, that's not a way that you can find out the shortest path. I mean, here you need to find out you need to apply the Dijkstra or something. You cannot just plug two shortest path in, and then you cannot say that, okay, since x2 is shortest and a to b is shortest, that's why x2b is shortest. No, maybe there is some path, let's suppose 3, or maybe something lesser. Maybe let's suppose this is 6, right? Or maybe 8, something like this. Maybe this is shortest. You don't know. So basically, you cannot plug two shortest, and then you cannot say that, okay, ultimately you are getting shortest. I hope you understood this. But the reverse is true, which means if you know that is shortest, then you take any of the pieces. You take any of the pieces that has to be shortest, right? Okay. So now, since this is known to be shortest, similarly, this is also known to be shortest. I mean, this is known to be shortest. This is known to be shortest. So you take any piece. This has to be shortest. This has to be shortest, right? Now, see here, this x to z has to be shortest. I mean, to go from x to z, since it is known that x to y is shortest like this, so this x to z is also shortest, isn't it? Which means the shortest distance from x to z must be x to z must be 10 only, because if it is lesser than 10, I will be in the trouble, because then the shortest distance from x to y will not be satisfied. So basically, if the shortest is given, that x to y is shortest, then you take any two pieces that has to be shortest, right? So shortest distance from x to z, I mean, at minimum you have to have 10 distance from x to z. So if this is 4, you cannot have 5 or something. You have to have 6 here, right? You have to have 6 here. Now my again question is that at least it has to be 6. Now can it be 7? My question was, can it be 7? If you put the 7 here, then if you want to go from x to z, then they are saying you go via w, then you will not be going via w, you must be going directly. So that's why it cannot be 7 also. It must be exactly equal to 6. Okay, I hope you understood. So that was really a nice question, right? I hope you understood this question. Okay, now let's see this question. This question is also quite a nice question if you just understand the pattern here. So what they're saying that f2n plus 1 and f2n both are same. Basically, they are not worrying about whether the number is even or the number is odd. They are saying let's not worry about the number being even or odd. You just go to the half. Okay, go to the half of it. Okay, if it is even or odd, does not matter. Go to half of it, and it will take just log n amount of work. It is same as saying this is n by 2 plus log n, isn't it? Maybe log n by 2 does not matter. This is same as saying something like this, right? So basically, this question is also a standard university question. Question is also standard question, and we like this question very much. The reason being is that once you find out, okay, this is the pattern that they are following, you can do it in the fraction of second. If you do not find out that okay there is a pattern, then maybe there will be a problem, right? I mean, you need to maybe solving it unnecessarily using the you need to unnecessarily unfold it. But otherwise, if you know that okay there is a pattern, then you can, I think, do it quite easily. So okay, let me just solve this question. I think now it is very much easy. You can apply the Master's theorem, right? So what does the Master's theorem says? It says that n power log, what is a and b here? B is 2, n power log base b a, right? So it is basically just 0 and then finally it will be 1. So 1 versus, you need to find out 1 versus log n. Since it is log n multiple, that's why the final answer will be log n into log n. That's what the Master's theorem says. In fact, it is theta of log n into log n. So that's why C is the correct answer. Okay, I hope you understood this. Let's go to the next question. Yeah, this was also sweet question. Very cute question. I mean, should have been solved in the examination by taking the examples. So they are saying that x and y are missing, and then you need to find out the x and y. So what you can do here? I mean, this is a question which I have taken from Stanford. So what you can do here? You can just see that how. I mean, they have also given that how you are doing it. You can just see that how you are actually doing it. Let's suppose that you have some number which is basically they're saying every number, everything that you generate from this is actually 0 point something, right? Everything that you generate from, let's suppose you have 0.1. In that case, this is 1 by 2. If you have 0.01, in this case it is 1 by 4, right? It is 1 by 4. Now they are saying that 0 is having 0 value, which means 0.0 basically it is having 0 value. 0.1 it is having 1 by 2 value. So 1 is having individually 1 by 2 value, and 0 is having 0 value. That's cool. Now they are saying 0b. If you are having, let's suppose, 0.0, b means, let's suppose if it is 1, right? Then what you will do? See, whatever this one's weight, which is 1 by 2. Now, in this case, it is actually 1 by 4. Because see, what is the value of 0.1? It is 1 by 2. What is the value of 0.01? It is 1 by 4. Which means if you're basically shifting it on the right, you are dividing by 2. So that's what they're saying. If you're shifting it on the right, so whatever the b1 value was, you need to divide by 2, right? So if you're shifting on the right, you need to divide by 2. Similarly, let's suppose this is 0.1, which is 1 by 2. If you put let's suppose 1 1. So whatever you have to basically you have to divide by 2, and then because of this 1 you have to extra add 1 by 2, right? But here you do not need to add 1 by 2. See, this 0.0.01, 0.11, both are exactly same because of this one. Because of this one, both will be having 1 by 4, 1 by 4. But here, because of the 0, you will not be adding anything. But because of this one, you will be adding 1 by 2. That's the only difference. So here, if you are having extra 1, you need to definitely add 1 by 2 plus whatever the weight of b1 or divide by 2. So b1 plus b1 divided by 2 plus 1 by 2, this is y. And then here you do not have 1 by 2. That's the only difference. So A and B are the correct answer. So Twinkle is saying, I did not understand that how you are basically doing it. Log. I'm not taking the log. I'm doing log n into log n. I'm not doing log of log n. That's the difference. Okay. So basically, this is followed by the Master's theorem. Master's theorem says that if you're comparing two functions, if one of the function is a log n time multiple, okay. Let's suppose that one function is n, another function is l log n. Okay. Then the final answer will be n log n into log n. Whatever is the bigger function, you take it and then into log n. That's what the Master's theorem says. Now here in our case, one of the function is 1, another function is log n. So you take, since the difference is of log n, you take the bigger function and then multiply by the log n. So that's what the Master's theorem says. I'm just applying the Master's theorem. Even in our course videos, we have even proved the Master's theorem. Is there anyone here that is a Go classes course student? So they can definitely tell you that we have proved the Master's theorem in our videos. I mean, intuitively we have done it, and that was really a nice proof. Now let's see this question. That question was also quite interesting. That question I just made it. Okay, I mean that question I made it by myself. This is very nice question. I hope you were able to do this question. Let me know if you want me to discuss this question. So what they are saying, that what is the maximum number that could appear at the first level. So this first level, whatever you are going to write, right? Since this is a min heap, then there must be 510 extra elements which are greater than this. So that's why I think the answer was 512, 513 or something, right? I think 512 or something. So the answer was something like this. Let me know if you understood this question, or there was some doubt in this question. Okay. So the explanation I have already given on the gate or flow, and that was our nice question. 513 was the answer, right? So 513 was the answer. This is the number that you can. Okay. So let me quickly discuss. See, there are 1023 elements, right? 1023 elements means what? That all levels are full. All levels are full. That's first observation that you can make with this number. Which means if this is root, then if all levels are full, then there will be exactly half of this, which is 511 elements here, exactly half of this, which is 11 element. Now they are saying what is the maximum number that could appear on the first level. Let's suppose this one. What is the maximum number that you can have here? Can you put 1023, which is the maximum actually? This is one, right? If you put 1023, then see, there are, the situation is something like this. There are on the left hand side 511 elements, which means there are 51 not elements below this. 51 not elements. Now, if you put 1023, then since the elements, all of these elements, whatever you are having, it is a min heap, must be greater than 1023. Since there is none of the element which is greater than 1023, that's why you cannot put 1023. Can you put some number which is like 3? Can you put some number which is like 3? Yes, you can definitely put 3, and then you will say, okay, see, there are 510 numbers which are greater than 3, that's why you can put it. But that's not interesting. We want to put the maximum number. So, what is the maximum number that you can put such that there are 510 numbers which are greater than this? See, this is 1023. Then finally, let me just subtract one. Getting so they, let's suppose this is 513. Now tell me, tell me, can you put 513? If you put 513, just verify that whether there are numbers, there are 51 not numbers which are greater than 513 that you can put. Yes, you can put, right? So basically, you can write 514 here, you can write 515 here, like that. You can fill this. You can fill this. You can definitely fill this. What about the right hand side? Right hand side also you can fill with the minimum numbers. I mean with the smaller numbers. See, starting from 513, 514 till 1023. These numbers you are putting it here, and then other numbers which are from this is one from 2 to 512. Definitely put here. Right? Maybe you can put 2 here, 3 here, 4 here, like that. You can put some. Okay. So I hope you understood this. Yeah. Okay. I will do this question little later. Let me just finish some of the interesting. Yeah. This is a very very nice question. Let's just do this question. How many of you were able to do this question? Let me know. This is very interesting question. Why it is interesting? Let me just explain this. Then you will get to know that why I'm saying this. So let me just explain this. How many of you were able to do this question? So they're asking us to run this particular function on the linked list. Now, just be with me. And then not you from this question you will not just learn this question, you will learn a very nice technique that how to do the recursion in case of linked list. Cool. So let me see if there is any other confusion, and then I will go to this question. Meanwhile, let me have some. Okay, so let's start now. Let's just see that how you can do this question nicely. So what they're saying that there is some head pointer which is pointing here, right? Now, if this head is null, if this head is null, you are returning, right? If this head is null, you are returning. Otherwise, you will check whether head data equal to x. Now, x is here 2, right? They pass with 2. If you check this question, they pass with 2. So they are saying that x here is 2. Okay, I think that's not visible. So the x is given to be 2, right? Cool. Let's just see this what they're saying. They're saying that if that is 2, then temp, you need to create a variable temp, and then you have to do temp equal to head next. Okay, let's just see that how to do it. What you will do, you will call this function, and then this is a linked list. Now this head, if you notice, this is a local variable, right? This is a local variable to this function call. Now currently I'm doing one function call. This head is local variable here. I mean, you have passed it, but I have copied the address in the local variable. Now what you will do, you will check whether the head data is x or not. Since it is not x, you are currently at 0, which is not 2. Then you will go to the else part. You will say that okay, now this head next, which means this pointer, see here, this head next will be pointing to mystery recur head next comma x, which means that now this will be pointing to whatever my next function call returns. So basically, this head, this head here is a local pointer which is pointing to 0. Notice here, this head is a local pointer which is pointing to 0, and head next is this. What I'm saying is that now this head next will be pointing to whatever I'm going to return, right? So basically, now you are saying that this link, whatever this link head next is pointing to, is actually broken, right? I mean, this head next is actually waiting. Now this link is broken. If this is waiting that whatever my next function call returns, and in the next function call I'm basically calling with head next, which means that in the next function call this head is actually again a local variable which is pointing to 4, right? So what I'm saying that now this function, this is waiting whatever my this next function returns. Suppose this next function returns null, then it will be pointing to null. Suppose my next function returns the pointer to this 4, then this will start pointing to 4. Suppose my next function returns the pointer to 6, this will start pointing to 6. Let me know if that is clear, that this is a head which is a local variable, because see, that's the local variable here, right? So it is a local variable. It is now waiting for next function to return whatever this returns, right? I do not know actually, currently I do not know what it will be pointing, right? I'm actually waiting. It is saying that okay, I'm waiting whatever you return me, I will point it out. If you return me null, I will point to null. If you return me pointer to 4, I will point to 4, something like this, right? Okay, so that's the thing that they are saying. Now just go here. Now this is another function call. This is another function call. Until now, this head next is still waiting. In the another function call, you say that okay. Again, you go to the else part, and then again you are saying that okay, let's just wait. Okay. Again, you are saying that you do not know where it will point to, right? So again, you are saying that you do not know where it will point to. You are saying let's just wait. Now, now there are another function call where the head is pointing here. Now this time, see, till now there are three recurrence. One is this, another one is this, another one is this. All of it are having its own local variable head. Let me know if that is fine to everyone. All of them is having its own local variable head, right? Okay. Is this understood how recurrence is working? And then what you need to do, you need to check that, okay, this is the head. Then since it is matching with the x, that's why it will say that, okay, now here locally, again locally, you need to create a variable temp, sorry, temp, a node, again a temp, locally, okay. This is again a local variable temp to this particular recurrence. And then you will say it will point to whatever head next is pointing to. So it will point to 4. And then you will free out this head, which means whatever head is pointing to, you will just remove this. You will remove this, right? And then you will return temp, which means then you will say that, okay, let me maybe go to the next page. See, 04246. This was 0, then 4, then 2, 6. This is my linked list. Now I came here. I'm saying that, okay, now this head, actually I'm just waiting for the for this 2.2. So I don't know where it is returning. So I'm just waiting here, right? This will point to whatever I return here. So this head pointing to 0 and head next is actually waiting. Similarly, here also head is pointing to 4, and then I'm saying that this is waiting, that whatever it gets actually waiting. This head next is actually waiting. Is this fine? Now I came here. I said, like, let's free this out. Temp is actually pointing here. Temp is pointing here. Temp is pointing to head next, right? Yeah. Whatever head next is pointing to. So temp equal to head next means temp is pointing to whatever head next is pointing to. And then I'm saying mystery temp comma x, which means I'm now calling the recurrence on this 4, right? Now, which means there is another recurrence where the head is pointing. See, these are the 3 recurrences. I mean, now there is another recurrence where the head is pointing, because I'm calling the another recurrence with temp, which is head next actually, which is pointed to 4, isn't it? Now till now is recurrence fine to everyone. The head next is waiting. Here head next is waiting. Here which one is waiting? Tell me. They are saying here anything is waiting or not? Let me know. So let me just, I think little bit you can see, right? So they are saying that there is nothing head next or nothing, right? There is nothing is waiting here. There is nothing is waiting here. So what you will do? They are saying return, which means at this function call. See, this was one function call, right? This was one function call. This one is one function call. This is another function call. This is another function call. I'm talking about the third function call. This third function call, they are saying they will return. See, they are waiting. And now they are waiting for, this is 2 is waiting for whatever this third return. 1 is waiting for that whatever the 2 return, right? They are saying that, okay, let me call for the head next, and I'm waiting for whatever the 2 return. So this 0 will point to whatever the 2 return. This 4 will point to whatever the 3 returns. Now 3 is saying that I'm not waiting. I will be just returning whatever earlier return. So what, see, this 2 is waiting for 3 to return. Now 3 is saying that I will just pass it out. Something will come to me. See, this will come to me. This result will come to me. I'm not waiting. I'm not saying my head next or something, right? There's some local variable head. I just feed it out. Okay, I'm just feeding it out. I'm not waiting for anything. What I'm saying, that I'm calling for the next function, which is 4, and then whatever it is returning to me, I'm directly returning same, which means I'm just passing it out. Whatever the 4 returns. Let's suppose the 4 returns are pointed to null. Okay, a 4 returns are pointed to null. Then it will just pass it out, and then it will start pointing to null. So basically, this 3 is saying that I'm just a mediocre. I'm just a not a mediocre. I'm just a intermediate person, right? So I'm not waiting for anything. I will just pass it out. Let me know if that is understood. Now it will call 4. It will say that, okay, my data is not 2, so I will do one thing. I will basically just wait, right? I will just break this link. I will call for the next, and I will just wait for it. Then similarly, again here, I will just break this link. I will call for the, now here, since I'm calling with null, then it will, this is the first time I'm returning null. Since I'm calling for the null, then since it is null, it will return null. So this is the first time I'm hitting my base case and I'm returning something. See, this is the third function call, then this is the fourth function call, this is the fifth function call, this is the sixth function call. In sixth function call, I got the null. Until now, everyone is waiting. This is waiting what the sixth return. This is waiting. What is 5 return to me, right? And what will the 5 return? See, see. Let's suppose this is the first function call. This is basically waiting whatever the second return to me, right? Whatever the second return to me. So basically, let's just hit this base case. I will explain this again. Let me first explain one iteration, then I will be having another iteration of explanation, because that's not a very straightforward question. Okay, so let's just see. The first time I'm hitting my base case, so now it is saying that it is waiting for whatever 6 return. So now I will be pointing out. Now let me go to the next page, and then now since it is returning, now this is the first time I'm pointing out whatever it is returning. I will start pointing to null, because it will return a null to me. It will return a null, because that's the base case it is saying. So I will start pointing to null, right? Now what this six will return, or the fifth function call will return, it will say that okay, see, it will say that okay, it will return head, right? It will return head. It will say that my head next is pointing to null, but head is pointing to 6, right? These are the local variables. It will return the pointer to 6, isn't it? It will return the pointer to 6, which means now this time I am saying, see, I got something from this. Now let me return a pointer to 6, which means I'm returning head, which means I'm returning this. Now again, this will return a pointer to, this head next got satisfied. Now this will return the head, which means the pointer to 4, which means it will return a pointer to 4 to this recurrence. But this 3 is saying that I'm not waiting. I mean, you have written a pointer to 4, which is nice to you. I mean, you are a nice person. You have written a pointer to 4, which is good. But now let's just do one thing. Let me just pass it out. Whatever you have just written, let me just pass it out here. So which means it has written a pointer to 4. It will just pass it out this pointer, right? Whatever it has written. So it will just pass it out this pointer, and then it will say that okay, let me let me just pass it out to this person, and then it will start pointing. It will also return head, so it will basically point to. So that's how my linked list is. Let me know if you have understood this, and also let me know if any of you have done using this method. If any of you done like this is the correct method. Okay, so even if you have not done it, then it is fine, like not an issue, but yeah, that's the correct method. So that's how we did it. Basically, this is called forward way. First, we are saying that okay, what is waiting, what is waiting, right? And then this is waiting, this is waiting, this is waiting, and then you start returning. Then you start returning. The 6 will return here. This will return here. This will return to this, and then finally you will return to this, right? So that's how it is happening. Do you want me to have one more example on the same? Let's suppose I do have 0, 2, 0, 4, 2, 6, 6, 2. Multiple times 2 is coming. 2. Let's suppose this is here. Now head is pointing here. Initially, it is a local variable. It will say, okay, let me just wait. Okay, whatever this 4 return to, right? I will be just pointing to whatever this 4 return to. And what this 4 will return to? Everyone is returning head, right? Okay, everyone is returning head. See here, everyone in the else part is returning head. Or if it is if part, then I'm returning whatever my earlier whatever the earlier function call is returning. Okay, Anamika, great. So Anamika is saying that she has used the same method. That's really nice. So has any one of you have seen one of my earlier lecture where I have explained on the YouTube the same thing, like how the recurrence works in the case of linked list? Okay. So now you come to this 4. Head is pointing here. Head is pointing here. Head next is waiting, right? Head next is waiting basically. Head is pointing here. Head next is waiting. Now you come to this 2. You say that whatever this is pointing to, just remove this, and then you call with the temp. Temp is basically head next. Now, which means the head is pointing here, and then it is not waiting for anything. It will just pass it out. Okay, whatever it will return, it will just pass it out, and then it will just wait. Again, it will wait. Head is pointing here, but head next will wait, right? Head next is waiting. Again, head is pointing here, but head next is waiting, right? But head next is waiting, which means this. Now it will come here. You will remove this, and then you will directly go here. So head is pointing here, but head next is waiting. Now this is null. Now this is the first time you will say that okay, head next is null, which means it will start pointing here, and then you will say that okay, you will return the head. Head means pointer to 3. You will come here, and then since it is just passing it out, you will just point it here, and then it will also return head, which means pointer to 6. You will point here. It will also return head, which means pointer to 6, and then it will pass it out, so it will point here. It will also return head, which means pointer to 4, and then finally you will be having 0 4 6 6 3. Let me know if you have understood this. Okay. Just hit the like button if you are getting the answers, so that that is how like people will get to know that this has some good explanation. Okay. So let me know if you have understood this question, or should you want me to explain this question. That was really a good question and easy question also. They are just asking few things. They are saying that which one will go to the deadlock and which one will not go to the deadlock, right? So you might have understood this from the explanation itself. There is a nice explanation that is given to this question. So let me know if you want me to explain this. Okay. So let's see this question. In this question, what they are saying, that the probability of the head is given to you. They are saying that the toss a coin until we get a head, right? So we need to toss a coin until we get a head. Which of the following is true? Now this C option, let's just see this C option. And before that, let me define. Um, okay, maybe I will define it later. So basically, or maybe let me just define. Let X be a random variable. You can define in any way. They are asking expected number of tosses for the first head. So just remove this expected, and then X will be the number of tosses. Number of tosses for the first head. Let's suppose this is your random variable X. And then what they have asked is expectation of X, right? And then you will say that they have asked this C. So whenever you need to define some random variable, then remove that X, the expected first. And then you will get to know that okay, how to define that random variable, right? Okay. So X is a random variable which is saying number of tosses for the first head. Now they're saying expected number of tosses for the first head. So they've asked expected. This is very nice question. Expected number of tosses for the first head. That's what they're asking, right? Easy one. So what you need to do, you need to basically check, okay, expected number of tosses for the head to come, basically something like this. You will do one thing. You have a coin, you will toss it out. Either head will come or tail will come, right? Or tail will come. If head is coming, you will say that okay, stop, because the head has come, and then till now the number of tosses was just one. This is the number of tosses, right? These are the number of tosses. Cool. Now if tail is coming, you will say, see, the tail has come, I wanted head, so I will restart my process. You will restart your process, and then you will say that okay, till now I have spent one toss. I have just spent one toss, and how many tosses I need more? Can you tell me how many tosses I need more? Let's suppose in total I need e tosses. Expect on an average I need e tosses in total to start with. Then since you're restarting, there is nothing you have gained with this particular toss, because you just got tail. So that's why you need e number of tosses, right? Again you will be needing e number of tosses. So what is happening here? You toss it out. Either you get head or you get tail. If you get head, you will be stopping. You will be saying that okay, now I got just one. I just need one toss. I mean, in one, I got my head. Like that's where I'm stopping, because I got whatever I wanted. But if you get tail, then you will be restarting, and then you will be needing one plus e more number of tosses. So basically, the situation is like this, that either you get head or you get tail. Here the expected number of tosses is 1. Here the expected number of tosses is 1 plus e. If e is the earlier expected number of tosses. So with p probability you will be getting head. With 1 minus p probability you will be getting tail. So there is a formula that says that expected number of expectation of any random variable is actually basically equal to the probability. Let's suppose there's some event A. The probability that event happens, and then expected number of expectation if that event happens, plus suppose that event doesn't happen, then what is the expectation. So basically there is some nice formula which is called total rule of rule of expectation. In fact, I have explained this formula in one of the video of the marathon. If you want, you can just check it out. Otherwise, let me just go very simply. So basically the expected number of tosses here will be, if you get the head, then with p probability you will be getting a head, and then how many tosses you will be needing here. With 1 minus p probability you will be getting the tail, and then with this probability how many tosses you will be needing here. So tell me, how many tosses you need here? Just one. How many tosses you need here? 1 minus e. So if you solve this out, let me just solve this out. This is e equal to p plus 1 minus p minus e plus ep. So this will be, it will get cancelled out. This is 1 minus e, 1 minus e, and then okay, I think 1 minus e, 1 minus e into minus p will be, that is fine. Take it that side. Okay, there's some mistake. This is p plus, just a second. P plus 1 minus p, you multiply 1 minus p here, 1 minus p plus 1 minus p into minus e, which means 1 minus p into minus e will be minus e plus ep, right? So it will be plus ep minus e, it will be minus e. Earlier also I think so this will get cancelled out. Okay, let me check. This is e equal to, I'm getting 1 plus minus e is same as 2e equal to 1 plus. That is not the same thing that I want, right? This p is the probability of the head. With p probability getting one toss, 1 minus p probability. Okay, so this is p into one toss with 1 minus p probability. Okay, this is 1 plus, sorry. So this is 1 plus e. Sorry about it. So I think calculation goes some. This is 1 minus p plus. So I hope you got it right. So till now, what we are doing, we are just writing simple equation where I'm saying that with p probability, you will be tossing one time. With 1 minus p probability, you will be getting 1 plus e time. So basically, it is same as p plus 1 minus p plus minus e. So this p and p get cancelled out. This e and this e get cancelled out. So basically, you have ep equal to 1, which means you have e equal to 1 by p. The expected number of tosses are actually equal to 1 by p. Let me know if you have understood this. Actually, I have solved this particular question using three methods. Using three methods in one of the video of the marathon. Okay, just watch out that video. Yeah, right, right. So this is 1 plus e. Has anyone watched out that video? Let me know. Using three methods, I did it. So anyway, like now you might not be having time, so don't worry about it. But you should be understanding this, right? So basically, 1 upon p is the answer. So that's why this C is the correct answer. But this C is not only used at one question. Have you seen some questions in the gate in computer networks also? They say that what is the expected number of packets you need to send? We need to send one packet. So basically if your success probability is p, whatever is success for you, maybe the coming the head is success for you, maybe sending packet is success for you. If the success probability is p, then you have to do 1 upon p trials. If the success probability is p. So we did it very nicely in one of the marathon video. Okay, I uploaded it. If you want, you can just watch it out. Anyway, so C is the correct answer, and this particular C option has been used at many places, not just in probability, but in computer networks, in many other places. Now, let's talk about the other options. What this option A is saying, that the probability the first head will appear on the second or the fourth toss, which means this X is basically the number of tosses. If the first head is appearing second tosses, the number of tosses will be 2. If the first head is appearing at the fourth toss, the number of tosses will be 4, right? Number of tosses will be 4. So basically, they're asking probability of X equal to 2 or X equal to 4, which means the tosses occur at the second toss. Head occurs at the second toss, which means does not occur at the first and occur at the second, or does not occur at the first three, or occur at the occur at the fourth toss. So that's one easy option. So you can just do it. A is the answer, C is the answer, and for B and D we did it. We did the easy derivation. So you just need to have the GP here, and then B and D is also the answer. We did it on the gate overflow, right? Okay. So let me know. Do you want me to just explain this B and D? We did it on the gate overflow. It is just a simple same summation, P into 1 minus P. I mean, if it x could be 2, could be 4, which means 1 minus P cube into P, could be 5, which means could be 6, which is 1 minus P into P power 5 into P, and then it is GP, right? And then finally you get the answer. Okay. Yeah. Now let's do this question. This question is very, very nice question, very interesting question. Let's do this question, what they are saying. Before that, let me know if you have any doubt in any of the question. Okay. Let's just continue. So this question is very nice. What they are saying that you have two grammars, right? One is S gives A, and then A gives, this is left recursive, which is capital A, small a. This is the grammar one. There is another grammar which is given like this. This is right recursive. Both are given to be the SLR grammars. They are saying that both are given to be the SLR grammars, and then they want us to solve for few options. So let's just see that how does the parsing happen. Let's suppose there is some string that I want to parse here. A. Let's suppose there is some string that I want to parse. Now, before that, I can draw the DFA, which is very easy to draw. So maybe I can just, okay. So let's suppose these are the two DFAs that I have. Now, what you will be doing? Okay, or let me just first focus on the first of one of the DFA here. So what you will be doing, you will be saying that okay, this is one of the DFA, let's suppose, and then you want to parse some string which is suppose a n times. Okay, if you are having some string, let's suppose a n times, then what you will do, if the first a comes, then you will go to this state, and then you will say that okay, then reduce it, right? Reduce it. Why? Because the next symbol has to be small a for the follow. Then since the next symbol is small a, because the follow of a is small a only, since the next symbol is smaller, you will reduce this. So what you will do, you will put this in the stack. See, understand step by step. You will first see this A. Okay. So this is basically your stack. This is input. Now here you have all A's. And then what you will do, you will check this A, and then you will say that okay, on this A in the initial state, I will shift it. So you will do the shift action, which means you will put this A, you will put this A here. So you will remove this A from here. Let me probably remove it. You will remove this A from here, and then you will put this A here. Let me know if that is fine. That is called a shift action. Okay. So this is called shift action. You shifted it. Now on this A, you will check that okay, can I reduce it? Yes, because the next symbol has to be follow of A, which is A, which is follow of A. You will reduce it. So you reduced it. Now on the next A, next small a, you will just shift it, because now see here. Currently, this is the configuration of the stack, and this is basically the input looking like. Basically, from the input you have read one A, and the stack is containing capital A. Now what you need to do, you need to rerun the DFA, which means on this capital A, actually you are here now, right? You are here. You are not at the initial state every time. You are, see, whatever in the stack, you are at which state? Initially, see here, initially there is nothing. So you are in the initial state. But the moment you have something in the stack, you are in that state. So now if you are having capital A in the stack, you are in which state? You are in this state. Now from this state, check if the small a comes, then what you do? You shift it. This is a shift entry. Now you shift it, okay? So you shift it, you shift this a also, and then you come here. Now just see very carefully. See how this parsing algorithm is working. You come here. Now what will happen? Now in the stack, what is there? Capital A and small a is there. So from the starting state, go from capital A and small a. Basically, you are in this state now. See, earlier there is nothing in the stack. You are in this state. You should know you are in which state. Then only you can parse it. Okay. So earlier you are in this state because there is nothing in the stack. Now you see A. You see A. You went to this state. Now you are in this state. Now you reduced it. See, let me just tell you step by step what is happening. This is initial, right? Tell me you are in which state. Let me just write the state here. Okay. See, once you understand that how the parsing is working, you will get to understand not just this question, but you will get to understand all of the parsing algorithm questions. So this is very important to understand. Current state. Let me just write the current state here. Initially, let me just call it state number 0, it is state number 1, it is state number 2, this is state number. Initially, you are in state number, always. You see small a, and then you write it here. So, on small a, you write it here, you shift it basically, which means you are saying, let me just shift. Now tell me you are in which state? Can anyone tell me you are in which state? After seeing this a, you shift it. Now you tell me you are in which state? This is little interesting. See, you are in the state. You are in the state based on the stack configuration. So what the stack contains is small a, which means you are in the state 1. The current state is 1. Now in this 1, you check, okay, there is a reduction possible. You reduce it to capital A. You reduce it to capital A. Now tell me you are in which state? Now tell me you are in which state? You reduce it to capital A and then tell me you are in which state? See, you always rerun the DFA. From this capital A, you will go to state 2, right? Now you are in the state 2. You are now in the state 2, always rerun the DFA. Now, from this state 2, you see the next symbol is A, you shift it, right? So, which means you shift it. Okay. So, from you will shift it and the stack will be containing capital A was already there and then you shifted the small a also. So, that's why stack will be containing capital A, small a. Now tell me you are in which state? Now tell me you are in which state? You have capital A, small a. You tell me you are in which state? You just rerun the DFA. Capital A, small a. You are in state 3. Currently you are in state 3. So how you are determining the state? Based on the stack configuration. Always rerun the DFA. Yes, there is optimization that you do not need to rerun the DFA, which means if you know that you are in state 2. See, here you know you are in state 2. Now from this state 2, you just save this state 2. Have you seen we write the state 2 here in the stack? You can save this state 2 and then from this state 2 you can have A and then you can go to 3. That's one of the way, but let's not worry about the optimization. Okay, first understand that what is happening. In this stack, whatever the content, you just rerun the DFA. This is a capital A, small a. Rerun the DFA, capital A, small a. Rerun the DFA, then you will be going to this state 3. Then that's why you are in state 3. Now, what you need to do, you see the small a here. What you are going to do on the small a, you say that okay, there is a reduction because if next symbol is small a, I mean in the follow of capital A, then you will reduce. You will reduce this to capital A. Now tell me you are in which state? Now tell me you are in which state? You reduced it to capital A. Anyone? In this particular configuration, you are in which state? Again, rerun the DFA. from the start symbol, you are in actually state 2. You're in state 2. You were in state 3, but then you reduced it, right? You reduced it. See, here you were in state 2, you see A, right? You shifted it, then capital A, small a, then you reduce this to capital A, then rerun the DF and tell me what is the state. So now you're in state 2. Now you see A, again you shift this A, right? Again you shift this A, then you will be having this something like this. Then this is capital A small a. Now tell me you are in which state? If you are having capital A small a, tell me you are in which state? Capital A small a, which means you are in state number 3. Now again you are in state number 3. And then state number 3 is saying just reduce it to capital A. So basically in stack, you are getting capital A small a, and then you are again and again reducing to capital A. So basically in the stack, you will be never be having more than two symbol, capital A small a, something like this, right? I mean, you have capital A small a, you reduce that to capital A, then you have capital A small a, you reduce that to capital A. Like that, it is keep on happening. So that is why the stack space is constant here. Getting my point? So basically, let me again explain this. What is happening? See, this is the grammar. You have A, right? You have, let's suppose this one. In the stack, you will be pushing A. You will be checking, okay, on this A, I will reduce this to capital A. Then you will be pushing, you have pushed this way, you will be pushing another A, capital A small a, and then on capital A small a, you will go to state number 3, and here also you will be reducing. Then again you see one more A, push it, right? Okay, every time you see this one more A, you push it. Then capital A small a, you will go into state 3, you will be reducing. Then again you see one more A, you push it. Then capital A small a, you will reduce it to capital A. Like that you will be keep on doing, right? So ultimately you just have two symbols. So that's why only constant space you are taking here. Only constant space. So here you are taking the constant space, right? Yeah. In this particular grammar, you are taking the constant. But in the next grammar, in this particular grammar, let me just take this particular grammar also. Here you are actually taking order of n. Why? Let me just show you. See, let's suppose you have a n times, right? On this small a, what you will do? You will push this small a here. Where you will go? You will go to, let's suppose this is state number 0, this is state number 1, this is state number 2, this is. You will go to state number 1. You will say that, okay, you will reduce only when the next symbol, this reduction will happen only when the next symbol is dollar. Since the next symbol is not dollar, you will do what? On the small a, you will just push it, right? You will push the small a, you will keep on pushing the small a, you will keep on pushing the small a. And the moment you push the last small a, at this last small a, since the next symbol is dollar, you will reduce this last small a to capital A. Then tell me, where will you in this stack? If the stack is this a, and the lastly you have reduced this to capital A, where in which state you are in now currently? Tell me, if the stack configuration is this, then in which state you are in? See, if everything is A and then finally you have the capital A, I understand that it might not be very much comfortable to you, because you might not have studied this compiler from Go classes. So basically at Go classes we have actually done it very intuitively. I mean, these things very intuitively, that how the parsing is working. But anyway, let's not worry about it. Let's not regret or something. I mean, let's be happy that you are learning it now. So what you are going to do, you are going to check in which state you are in. Basically, you are going to see how the DFA works. A and then all A's you will be here, and then after this capital A, you are in the state 2 now, right? You are in the state 2. Yes, you are in the state 2 now. So in the state 2, you will again reduce this thing to capital A. And then again you are in state 2, you will again reduce this to capital A, and again you will reduce this to capital A. Basically you will keep on reducing to capital A, and then finally you will be having this, you will again reduce this finally to, right, small a, capital A. And then the capital A, you will go to the state 3, which means you will reduce this capital A to S, and which is the accept state, So you will be having order of n space or theta of n space in this case. This was very, very nice question. If you have understood this, very good. Let me know if you have understood this or there is some doubt. Then only I will move forward. Let me know if you have understood this correctly. Okay. So let me move further. Now, one of the last question that I want to solve is this. Okay. And I wanted to solve this question also, but I think that is doable. Which one? That CN1, right? So that was a nice question that we have framed. So I mean the wordings and all, like I kept it very nicely from different resources. I framed this question, and this is one of my favorite question. Reason being is that maybe I framed it from different resources. I made it very clear this question, right? Okay. So let's just do this question, which is a cache related question. This is also an easy question, but let's just do it. Cool. So what they're saying consider the following code that access the two-dimensional array, okay, which is having 64 into 64 integers, which means there is two-dimensional array which is having 64 into 64 integers, which means that let's suppose the array is a64, I mean int a64, which means this is a0. I mean, A00 is this, A01 is this, A02 is this. I mean, anything that is starting from A0 is this. Similarly, this is having 64 integers. Similarly, in the memory, it will look like this, right? It will be A1. Similarly, there will be A60. So in the memory, it will look like this. Now, let me go to the next page. Let me just do this question nicely. So for these type of questions, what you first need to do, you first need to check that how does it look like in memory? How does your array look like in memory? So let's just first see that how does your array look like in memory. Which means since the memory is one dimensional only, even though the array is two dimensional, so your array will look like this. This is A0, A1, right? Okay. And then what do you have here? They are saying that you are accessing elements like A00 and then A01, something like this, right? So let's just see how big your cache is. Your cache is directly mapped 1 KB cache, 16 byte block size. So 1 KB cache means in this cache there are how many blocks? Number of blocks. Number of is 2 power 10 bytes and 16 to power 4. Means 64 blocks will be there. These are the 64 blocks. Each block is 16 bytes, which means each block can hold 4 integers, right? Each block is 16 bytes, means each block can hold 4 integers. Now, these are the 4 integers which will go to the first block, right? And since there are 64 integers, what will happen? It means 64 integers means that how many blocks? So they will take one block is taking 4 integers. They will be basically taking one and then two 16 blocks, right? So basically, it will be this particular will be eating up 16 blocks. So you need to check two things. One is that how many like how does your array look like, and then each array basically here you are having 16 blocks, which means the first four integer will map to the block number 0, next four integer will map to the block number 1, like that, and then this is again 16 blocks, like that. Okay, no problem. So what you are going to do, you are going to access this particular integer. The moment you access this A00, see here, the moment, since these are the 16 blocks, the moment you access this A00, and each block is basically containing 4 integers, you will be putting all of these 4 integers in this cache, right? Now, in this particular block, you have the 4 integers, which are A00, A01, A02, A03. Now, again, you are accessing A01, A02, A03. So, out of these 4, you are just getting miss on 1, which is a compulsory miss. Right? Because nothing is there. So, definitely you will be missing 1. Then, but for these 3, you are not missing anything. Now, again, for this block, you will be missing on this. This will map to the next block, and then you will not be missing. So after the first iteration, when A0 is accessed, right? Your see after the first iteration, in the first iteration you are accessing A0, in the next iteration you are accessing A1, similarly you are accessing A63. So after the first iteration, your A00, A01, everything which is taking 16 blocks, right? Which is taking 16 blocks. So 16 blocks will occupied. Similarly, after the next iteration, next 16. After the next iteration, next 16. After the next iteration, next 16. So basically, after A3, this is A2. After A3, your all of this 64 blocks will be occupied, isn't it? Now, once you access the fourth or fifth iteration, which is A4, which is again mapping to the first block or something like this, then that is okay. See, I mean, again, either it is full or occupied, doesn't matter. See, earlier for these particular accesses, I was getting the blocks were free. I mean, I can map it. But now for A4 will map to whatever this A0 map to. That is fine. Reason being is that like I do not care that earlier it was free or occupied or something like this. So basically these are let's suppose 16 blocks. So this A4 at the first axis it will get mapped to the first block of the 16 blocks. Anyway, I do not care. In all the cases, this I'm getting miss on only the first element, right? And all of these are free. So out of four axes, on average, I'm getting miss on just one, which means 25% is just my miss rate. Okay, so that's how you can solve this question. 25%, easy question only. We kept it. I mean, that was a nice question, gate relevant question, but we have kept it easy. Let me know if you have understood or there is some doubt. Okay. So thank you everyone. Take care. And before I go, let me just suggest you something that how you should be preparing. I mean, not the preparing, but how you should be preparing your mindset basically. Now see, only 2 days are left, so I will just suggest you that you should not be obviously worrying about anything. Whatever has happened has already happened. Now you need to just prepare your mindset in such a way that you have to give your best, which means that don't think anything that is beyond your control. Just think that whatever you did, that was good or bad, doesn't matter. Actually, doesn't matter. Maybe bad. I'm not saying that it was very good or something. Everyone has done some mistakes in the past. That's perfectly fine. But now, what you should be thinking is that performing in the best way, even though your preparation was the worst. Honestly, like I mean, when I was appearing for the gate examination, at just 1 hour before the examination, I was thinking that okay, maybe my preparation is not good. But suddenly I started thinking because I got a call from my brother and he was saying that okay, you should be performing very good in the examination. So I started thinking that okay, no, whatever I have done is okay, I have to perform best in the examination. So just go with the mindset that okay, my preparation was whatever. Maybe you have just studied only 1 day or maybe 1 year. You have studied maybe 1 month or maybe the entire 1 year. Does not matter at all. You have to perform your best in those 3 hours. That's the mindset you should be keeping while you are going for the examination. So that's all I want to suggest from my side, that you should be keeping a very open mindset, that okay, you should be going with the 100% clarity that you should be performing your best. Whatever you have done does not matter, but you should be performing your best. That's only you should be keeping it. Thank you everyone. We will be meet again. We will be conducting session where me and Deepak will be there. If you have any doubt, you can ask, or otherwise like we will be just suggesting some last tips that you should be keeping in mind, such that you convince your mind that you should be performing.